Good morning, everyone. My name is Bhanuka Mahanama. Today, I'm going to present our paper titled Unsupervised Domain-Adaptation for Appearance-Based Gaze Estimation. Now, let me start with the question, what is gaze estimation? Now, gaze estimation can be simply defined as approximating the gaze portion of a person. Now, in the case of the gaze portion, we can represent it in terms of point of gaze or in terms of gaze directions. Now, this has wide variety of applications. Now, these applications include human-computer interaction, psychology, and market research. Now, in the case of gaze estimation, we can do it in different types of techniques. Now, one of these techniques is appearance-based gaze estimation. So here what we do is we use commodity hardware like web camera, as you can see in the image as well, to capture the facial or ocular images of a user. Now, using those facial or ocular images, we use deep learning techniques to identify the point of gaze or the gaze directions. Now, why do we need domain adaptation? Now, if we consider the environments we do gaze estimation in, these different environments vary significantly. As a result, we have different types of input domains. We have controlled environments, such as laboratories, semi-controlled environments, and also on top of that, we have uncontrolled environment or in the wild environment. Now, the problem here is we are using a deep learning model. As a result, if we want to get better cross-domain performance, we need to train or provide the model with examples from all these different input domains. Now, to do that, we need to collect and annotate a dataset, a large dataset which contains examples from all these domains, which is not going to be feasible. So our solution to this problem is unsupervised domain adaptation. Now let's start with how we can our problem formulation for our unsupervised domain adaptation. Now here we start with the gaze estimation model built using an autoencoder. Now what it does is it uses an encoder and it produces a latent space. Now we split this latent space between gaze defining features and non-defining features. Now in the case of gaze defining features, we use gaze defining features to estimate the gaze directions. Now in the case of non-defining features, we combine them with the gaze defining features and produce a reconstruction of the image. Now, in addition to that, we also incorporate adversarial domain adaptation. So what we're trying to do is we are trying to enforce this encoder to produce a representation, which makes us harder to distinguish between different domains. Now, to do that, we have two domain conditions. We have the label source domain, and we also have unlabeled target domain. Now, how does this fit into our model architecture? Now, in our model architecture, we have image reconstruction and gaze estimation. In addition, we also have the domain classifier. What does this domain classifier trying to do is, it uses the latent representation generated for an image, and it uses the latent representation and tries to figure out whether that image belongs to the source domain or the target domain. Now, in the training, what we do is we reverse the gradients coming in from the domain classifier. Now, this forces this encoder to produce a representation which makes the domain classifier harder to distinguish between different domains. Now, in addition to that, we also have the reconstruction and the gaze estimation. Now, these two also forces this encoder to produce a representation which is helpful in the image reconstruction and also in the gaze estimation. Now we have three functions happening in our gaze model. We have classification, reconstruction, and estimation. So we have three loss terms in our loss function. We have the domain classification loss, reconstruction loss, and the gaze estimation loss. Now let's see how we can combine these. Now to combine these loss functions or loss terms, what we do is we introduce two hyperparameters, lambda r and lambda c. Now lambda r is applied to the reconstruction loss and lambda c is applied to the classification loss. Now in our training, we train this model in two steps. The step one, or we call it as source training, we provide the model with label source data. Now here, what we do is we train the model using only gaze loss and the reconstruction loss. In the second step, or in target training, what we do is we give the model with label source data and also unlabeled target data. Now, in the second step, we use the combined loss function to do the training. So we have three terms in our loss function. Now, as the labeled source data in our experiments, we use XGAS dataset, and as the unlabeled target, we use either GAS 360 or RTG. Now, in our first experiment, we trained and evaluated the model on XGAS dataset, or we just did the source training. Now, for these experiments, we use three models of different sizes derived from the efficient net version 2 base model architecture. We have the small model with 6.2 million parameters, medium model with 9.2 million parameters, and the large model with 13.4 million parameters. Now, in the case of our in the case of our models, generally they have comparable performance against the XGS baseline, which has 4.5 degrees of error. Now, if we compare them along with the number of parameters, our smallest model uses only 76, our smallest model uses 76% less parameters while getting only 10% hit on the accuracy. Now, in the case of our largest model, it still uses 14% less parameters, but only with 2% hit on the accuracy. Now, in the case of smallest model, when we compare with a similar size model, like efficient net version 2 baseline, our model still achieves a better performance having similar number of parameters. Now, in the next experiment, we perform target training using the GAS 360 dataset. Now, after target training, we evaluated the model performance on GAS 360 dataset and also on the RTGene dataset. Now, for both RTGene and GAS 360 dataset, if we consider our small model, unsupervised domain adaptation generally improves the GAS estimation error. Now, if we consider the scenario of having the combined loss function, that means lambda z is not equal to 0, you can see in all these cases, it yields our unsupervised domain adaptation yields to better error. Now, in the case of the medium model, the combined loss also leads to improvements in the GAS estimation error. But in the case of our large model, we did not see any such improvement in both datasets. Now we can visualize these GAS improvements using samples from the GAS dataset. Now here we have GAS corrections or GAS improvements for GAS 360 along with samples from the GAS 360 dataset. Now here we have visualized the corrections when we trained with the combined loss function with lambda r and lambda c equal to 0.1. Now in the images, you can see in red the GAS estimations before domain adaptation. In green, in blue, you can see GAS estimates after domain adaptation, and in green, the ground truth. As you can see across these images, after domain adaptation, the GAS estimations have better alignment with the ground truth. That means it has corrected after the domain adaptation. Now, the important thing to notice in these GAS corrections is that these GAS corrections or improvements are achieved by simply providing the model with example images from the GAS 360 dataset. So the model has no idea about the labels, but it has seen just the images from the GAS 360 dataset. Now it has improved the GAS estimation error. Now we can do a similar visualization for the GAS RTGene dataset as well. Here we have used the model with domain adaptation on GAS 360 with similar colors representing the domain estimates before domain adaptation, after domain adaptation, and the ground truth. Now in these images as well, you can see the estimates after domain adaptation is better aligned with the ground truth. Now, the most important thing to note here is that these corrections are achieved by the model even without seeing a single image of the RTGene dataset. That means it has corrected the GAS estimations on unseen domains as well. Now, to further evaluate the cross-domain performance of our model, we conducted 2 more studies using our models without doing any modifications to our domain-adapted model. Now, here we use 2 datasets. We have GAS directions using Columbia GAS dataset and also smartphone GAS estimation using the RGBD dataset. Now, for the models, we use the smallest model, our small model with case 360 domain adaptation. And to have a benchmark, we use the small model without any domain adaptation and a similar size baseline of efficient net version 2. Now, in the Columbia Gas dataset, the best performance is achieved by lambda c equal to 0.1. That means the model trained with the overall loss function. Now, in the case of when we are training models without the loss function or the combined loss function, we can see it did not improve any error. So that means the discriminative classification is to better performance in the Columbia Gas dataset as well. Now, in a similar manner, we can also visualize the gas corrections on the Columbia Gas dataset as well. Here we have in red the estimates before domain adaptation, blue estimates after domain adaptation, and green the ground truth. Now here also we can see the domain adaptation has led to better alignment of the case estimates. So here also, similar to RTGene dataset, is what we can say is the model has been able to correct the gas estimates even without seeing any image from the Columbia Gas dataset. So all the model has not seen any image from the Columbia Gas dataset or any labels. So our approach has corrected gas estimates on unseen domains as well. Now, in the next experiment, we evaluated the model performance on the smartphone gas estimation. Here, what we did was we used the gas directions combined with the user distance to estimate the gas location. Here, we used a regression and we determined the parameters of the regression using a 5-point calibration. So we have as the 5 points, we use the 4 corners and the center. And for each calibration point, we randomly sample 2 to 15 samples from the dataset. Now, in the results, our domain adapted model has come with the combined loss function has better performance across all the number of parameters, calibration number of parameters, number of samples per calibration. At 3 samples per calibration, our model already outperforms the tablet case dataset or the tablet case baseline. At 15 calibration points per 15 samples per calibration point, our model achieved a gas estimation error of 2.72 centimeters. Now, if we compare with similar experiments like ITAB or RGBD gas data, our model does not have better performance. But the important thing here to note is our model has just seen few samples from the dataset. It has not seen all the images from the dataset. It has just seen 15 samples per calibration point at this point. So what we can see is, we can say unsupervised domain adaptation also eliminated the need for large-scale mobile gas data asset as well. Now, this brings us to the summary of our presentation. So in summary, what we discussed today is we discussed about the domain shift in gas estimation, which required the large scale dataset. But the thing is, we provide a solution to this problem through unsupervised domain adaptation. So here we combine unsupervised reconstruction and adversarial domain classification to provide our solution. Now, in terms of our performance, in the case of our approach, it improved the gas error in seen labeled datasets, unseen unlabeled domains, and dissimilar unlabeled domains as well. So in summary, what we can say is our approach has eliminated the need for large-scale target domain datasets. Now, this brings us to the end of presentation, and thank you. If you have questions, you can ask now.